Hi everyone, today we're going to get started with chapter 7. So in the beginning we're going to talk a little about the alkene structure. So this mostly should be review from chapter 1. So let's look at ethylene. So the formula for ethylene is C2H4. When we look at ethylene, each carbon atom is going to be bonded to 3 other atoms. So it's bonded to 1 carbon and 2 hydrogens. We have sp2 hybridization when we're looking at something like ethylene. So we have our sp2 orbitals shown here. Then we have our unhybridized p orbitals shown here. So the pi bond in ethylene is going to be formed by the overlap of our unhybridized p orbitals. Remember that pi orbitals or p orbitals must be parallel to each other. We have half of our electron density below the plane and half of our electron density above that sigma bond or the plane. And when we're looking at the electrostatic potential map, we can see a high amount of electron density, which is shown in red right here, which is given rise by those pi bonds. When we look at the alkene structure, so looking at ethylene versus ethane, so we look at our CH bonds. So when we're looking at the CH bonds, the CH bond length, so the 1.08 in ethylene is slightly shorter than in ethane, so the 1.09 angstroms, because the sp2 orbital, so we have ethylene is sp2, ethane is going to be sp3, so this is basically 1/3 S character and sp3 is going to be 1/4 S character. So the sp2 hybridized orbital just has more S character, which makes sense why that CH bond would be slightly shorter. When we're looking at the carbon double bond carbon, it's much shorter than the carbon single bond carbon. So we have 1.33 versus 1.54. And really, if you think about it, this makes sense because we are looking at the sigma bond formed by sp2 hybridized orbitals, which would have an angle of 120 degrees, versus the sp3 orbital, which would have an angle of 109.5 degrees. When we look at the cis trans interconversion, so we looked at rotation amongst bonds. I can't remember what chapter, probably chapter 1 or 2. And when we look at ethylene, we do have that double bond, and we can see that it cannot be twisted without disrupting that pi bond. So again, remember that we can rotate amongst sigma bonds, however, we cannot rotate amongst pi bonds. So if 2 groups are on the same side of that double bond, again, this would be called cis. So again, 2 groups on the same side, that would be cis conformation. We cannot rotate those to the opposite side to get the trans conformation without breaking that pi bond. So let's look at some general naming just so you're familiar with different terms when you hear them in maybe Orgo 1 or if you're continuing on to Organic 2. So for alkenes, we're going to use the same root name of the longest chain. So we talked about propane, ethane, butane. So all of those root names are still going to be used. However, the ending is going to be changed from ane to ene when it contains a double bond. So ethane, for example, is going to become ethene, propane would become propene, cyclohexane would become cyclohexene. So when the chain contains more than 3 carbon atoms, the number is going to tell us where that double bond is. So the chain is going to be numbered starting with the n closest to the lowest number. So if we look at, so there's some old IUPAC names and some newer IUPAC names. Honestly, you'll probably see both of them still used in most textbooks. So with the old IUPAC names, we have, if we're looking at this first example right here, we have a 4 carbon chain system. So we know that we would use the root name butane. However, we do have a double bond, so we're going to change that ANE to an ENE. Our double bond starts at the 1 position, so we will call this either 1-butene or but-1-ene. Again, with this example here, we have a 5 carbon chain, so we would think of pentane if this was a simple alkane. However, we notice that we have that double bond between carbon 1 and 2, so we would call this 1-pentene. Again, you just change that ANE ending to an ENE ending. When we look at our cyclohexane ring, so we have a 6-membered ring, we do have a double bond between carbon 1 and carbon 2. So you could write just cyclohexene. It could technically be written as 1 cyclohexene. It's just not commonly written like that. When we put the double bond between carbon 2 and 3, when we have a 4-carbon chain, now the name would just be 2-butene. Same thing for pentane, or for this chain right here. So we have a 5-carbon chain. This time we're putting the double bond between carbon 2 and 3. So we would just call this 2-pentene. When we're looking at more than one double bond in a molecule, if we have 2 double bonds, we're going to call them a diene. So in this example, we have a double bond here and a double bond here. So we have a 4 chain, so we know we would use butane, but what we're going to do is we're going to switch that ending to a diene. So diene just means that we're going to have 2 alkenes. So again, the numbering is just going to be where that double bond starts. So this one would be 1,3-butadiene. The same thing if we have 3 double bonds. So here we have a double bond here, here, and here. So instead of diene for 2 double bonds, we call this a triene for 3 double bonds. And again, you're just going to count the longest chain. You're going to use that root name, and then you will just use triene and make sure that you're using the proper numbering scheme. So again, you want your first double bond on the lowest possible number. And then same thing with a cyclic system. So if we have more than 1 double bond in a cyclic system, you just count the number of double bonds. So here we have 4 double bonds. When we have 4 double bonds, it's going to be a tetraene, right? Which makes sense. So di for 2 double bonds, tri for 3 double bonds, and tetra for 4 double bonds. Again, you're just going to number those, and then you will put everything together. So this would be 1, 3, 5, 7 cycloocta tetraene. Sorry. So again, you won't be tested on anything with naming, but it's good to just be familiar with the different naming. So when you're looking at molecules, either in a lab setting or in the textbook, that you know what molecule is in question. So let's look at the stability of alkenes. So this part is going to be a little bit new. So stability of alkenes, we often see the major product is going to be the most stable alkene, which really makes sense, right? So when we can compare the stabilities of these molecules, of these alkenes, by converting different compounds to a common product and compare the heat that is given off. So the most common way to do this is by looking at the heats of hydrogenation by using reactions similar to what is shown on the slide here. So with hydrogen in the presence of a platinum catalyst. So combustion could also be used, but combustion isn't really reliable. It's just, there's a lot more room for error. So again, the reactions similar to the conditions shown on the slide are what are typically used to measure the stability of that double bond. And then the most accurate comparison between different alkenes, the stabilities between different alkenes, occurs when they produce the same product in the hydrogenation reaction. So that would be something that we're looking at above. So in both, we're producing butane as our product. When we're looking at the relative heats of hydrogenation, so hydrogenation is usually going to be exothermic. So when we're comparing the heats that are released from the alkenes in these hydrogenation reactions, the more heat is going to imply that the alkene is going to be more unstable. So you have to think of this. It's going to be starting from a higher potential energy. So in general, we're going to look at this on the next slide, but the more substituted alkene is always going to, almost always going to give you the more stable product. So this is going to give off less heat in the actual hydrogenation reaction. So if we look at the relative stability of alkenes, so looking at the slide right here, so these are all going to be compared to, these are the relative rates in comparison to ethylene. So you can see that the more stable is going to be our tetrasubstituted followed by our tri-substituted, and then we're going to go through. So trans is going to be more stable than cis, for example. Mono-substituted would be more stable than ethylene, which is just an unsubstituted molecule. So if we think about this, so let's kind of break all of this down. So when we're looking at an alkane, these are going to be separated by a tetrahedral bond, right? So we have 109.5 degree separation. If we have a double bond, this is going to increase this separation to 120 degrees. So it's really pushing these methyl groups further away from each other. So the steric effect is shown on the slide here, right? When we have, so this is going to be more substituted. We have 1, 2, 3 groups basically coming off of that double bond versus 1, 2 groups coming off of that double bond. So again, the more substituted isomer is just going to have a larger angular separation between those bulky R groups. In this case, they're just the methyl groups, but again, it's still pushing them further apart, wider separation. If we think about the cis, geminal, and trans, so remember geminal just means that we have the 2 R groups coming off the same carbon. So something like this would be considered geminal. Typically geminal is actually harder to, it's not very reliable. So really what we're going to be looking at is going to be cis and trans. So trans is going to be more stable, which again makes sense if you think about it, because these are going to groups, these R groups are going to just be further away. So they're just separated further from each other. So again, trans would be more stable than cis, for example. When we look at cycloalkenes, so we talked about rings in, I can't remember, I think it was chapter 3 maybe. So when we're looking at rings, we talked about three carbon membered rings and 4 membered rings. So there's a lot of strain associated with both of those types of rings. So if you think about it, it's going to be really hard to put a double bond in a small membered ring. So again, a 3 or 4 membered ring, because there's already so much strain associated with it that this is going to create additional strain, which is making them much more reactive than the normal alkene. When we look at rings that are 5 membered or greater, they can usually accommodate the double bond that are less strained, and they will behave like normal, so straight chain alkenes. We can have trans double bonds in rings with 7 to 9 membered rings, but again, it's hard to add a trans double bond when we have 3 to 6 membered rings, again, just because of all the strain associated with that specific cyclic system. If we look at alkenes in bicyclic systems, so a trans cycloalkene is not stable unless there are, again, at least typically 8 carbon atoms in the ring. Another term that we have to talk about is going to be bridgehead carbon atoms. So what a bridgehead carbon atom means is it means that we have 3 links connecting them. So if we look at this carbon right here, this is a bridgehead carbon, so it's connected to 1, 2, 3 different carbons. If we look at this carbon right here, this is considered a bridgehead carbon because we have 1, 2, 3 different carbons that it is attached to, or 3 different links connecting them. So when we think about these bridgehead carbons, we have a rule called Brett's rule. So a bridge bicyclic compound cannot have a double head at that bridgehead position. So this is going to put that double bond in the trans position. And again, trans position is not very stable when we have a cyclic system. So it is stable in some ways if we have a larger ring. So again, something with a 7 to 9 membered cyclic system. So when we look at this molecule here, our double bond is not at a bridgehead carbon. So this is going to be a stable molecule. This would actually be in the cis position. When we look at this molecule here, so we're putting this double bond on a bridgehead carbon. Again, the bridgehead carbon is going to be right here. So this double bond is actually in the trans position. So this is going to be a very unstable molecule. When we look at this molecule right here. So we're putting the double bond again on a bridgehead carbon, but the difference here is we have more than an 8 carbon system. So this would actually be a stable molecule. So that's really a review on alkenes in general. Some of this is new. Again, just thinking about probably like the bicyclic systems would be the newest part. Everything else is really just the more substituted the alkene is, the more stable the product is. And again, trans is going to be more stable than a system. So now let's really get into the reactions for chapter 7. So we're going to start with an elimination reaction. So in an elimination reaction, a proton and a leaving group on adjacent carbons are going to be lost to form an alkene. So we have our substrate, we have our base, so your base or your nucleophile, those terms can be used interchangeably. We have our elimination product. We have our conjugate acid, and then we're going to have our leaving group. So when we look at the elimination reactions, first we're going to talk about the E1 reaction. So with the E1 reaction, what happens is we have the loss of that HX in a 2-step process. So the first step is going to be our rate determining step. And we are going to have the formation of a carbocation. So the E1 is going to stand for elimination, unimolecular. Again, so this is where our E and then unimolecular is telling us 1. So this is where that E1 is coming from. So a lot of this should sound familiar to you when we talked about substitution reactions, right? So our first step in a substitution reaction is the rate determining step, and our first step results in the formation of a carbocation. So when we have E1 reactions, in most cases, we're going to have a mixture of both elimination and substitution products formed. Again, because they are competing with each other. So we have, let's look at a E1 reaction. So if we have something like this, so we have our leaving group on a tertiary. The reaction is done in water. What our product would look like is going to be the formation of that double bond. So when we have the formation of our double bond, we have to think where that double bond is forming. So we would have the double bond forming. So this carbon right here that the leaving group is attached to is going to be called an alpha carbon. And then any carbon that that alpha carbon is attached to is going to be called a beta carbon. So when we're looking at elimination reactions, it's also called beta elimination a lot of times. So you can remove a proton from a beta carbon, and that's how you're forming that double bond. So when we look at this reaction, so we have this substrate, and the reaction again is done in water. We have this product here for our E1 product, and then we would have this product here as our SN1 product. So let's look at the mechanism for these reactions. So SN1, I know everyone is really, really comfortable with, so let's start with the SN1 reactions. So SN1 reaction, when we look at this mechanism, what's happening is we have our leaving group, leaving. So we're going to have the formation of that carbocation. Again, it's on a tertiary carbon, which is ideal. Then we're going to have the attack of our nucleophile, or water in this case, at our carbocation site. So remember, water is going to act as a base, and it's going to deprotonate one of those protons to remove that formal charge, that positive formal charge from oxygen. And we would be left with our SN1 product. So the first step is going to be the same for the E1. So elimination, E1, or beta elimination. All of these terms are used interchangeably. So we're going to have our substrate. plus water. So again, water is going to be our base or our nucleophile in this reaction. So we're going to have dissociation or formation of our carbocation. So our carbocation's at this position here. So remember, this again is our alpha, wherever the leaving group is attached. This would be a beta carbon, beta carbon, beta carbon. So really any of these protons could be removed. I'm just showing it on this methyl group right here. So our water again is going to act as a base. So what's going to happen is it's going to deprotonate one of these protons from the methyl group. These electrons are going to go here to form our double bond, and we would be left with our elimination product. So again, the carbon from which a proton is removed is going to be called the beta carbon, and the beta carbon is always attached to that alpha carbon. So both of these types of reactions, so SN1 reactions and E1 reactions, are going to occur rapidly with very little selectivity, which makes sense if you think about it, because their rate determining step is that formation of that carbocation. So after the formation of that carbocation, it's going to be really hard to control what happens, because the SN1 and the E1 reaction are going to happen almost at the same time. Neither SN1 or E1 is really a practical reaction, just because there's so many different products that are produced. So remember, when we have an SN1 reaction, if the nucleophile is attacking that carbocation and it's making a stereocenter, we're going to have an inversion product, we're going to have a retention product, and now we would add a lot of different E1 products also to the system. So if we have different beta carbons, for example, we can form a lot of different E1 products, which we're going to look at in a couple minutes. So when we look at the rate equation for an E1 reaction, I hope that in your head you're thinking about the rate equation already. So the rate equation we know is going to be first order overall, and it's going to be first order in respect to the substrate. So, which makes sense, right? Because this is the same rate order as what we saw for SN1 reaction. So again, the nucleophile or the base is going to have very little effect on the rate of the substitution or elimination. So we will see poor nucleophiles typically used for SN1 E1 reactions. So this is a good indication that if you do have a weak or poor nucleophile, that it will proceed via E1 SN1. And at this rate, we would expect you guys to show all products, so all substitution products and all elimination products. When we're looking at the selectivity of E1 reactions, so we're going to look at processes for bond formation favors, or I should say favor of bond formation. So if we have a E1 reaction and there's more than one type of beta hydrogen. So let's look at this example here. So if the reaction is done in water with, let's say, a little bit of heat. So we're going to have the formation of our carbocation. And now we have to think about all the different hydrogens that we have. So we have HA here. We have an HB hydrogen here, and we would have an HC hydrogen here. So we have a lot of, so again, this would be our alpha. So this is going to be a beta, this is going to be a beta, this is going to be a beta hydrogen, or sorry, beta carbon. And then we're looking at all the hydrogens attached to that beta. So if we remove HA versus if we remove HB versus if we remove HC. So when we remove HA, what happens is we have the formation of this product here. So we'll call this A. When we remove HB from the system, we're going to have the formation of this product here. So this is going to be cis to each other. We would also have the formation of the trans product. So again, this would be B trans. And then if we remove HC, so HC, this would be the removal of HC, we're going to be left with this product here. So we have a couple different terms when we're looking at the selectivity of these reactions. So we have the Zaitsev product. So Zaitsev product is going to be A in this case. So this product is going to be the most substituted alkene. And this is probably most typically favored in a elimination reaction. We also have a Hoffman product. So the Hoffman product is going to be the least substituted alkene in the product. So here this would be C, would be the Hoffman product. So again, you can see how the formation of several different products would be present in a reaction, because with this reaction, we would also have our substitution reaction, so our SN1 products. So again, there's a lot of different products that can form in a specific reaction. So really what you want to think of is, again, think about your substrate, think about your nucleophile, and think of which way that this process should be proceeding. So if it's proceeding SN1, it's also going to proceed via an E1 reaction. So we're going to stop right here. So again, just kind of give yourself a refresher on alkenes in general, and then look over the E1 reactions. When you're working on E1 reactions, again, make sure that you're thinking about the SN1 products also. And then our next lecture, we will start looking at the E2 reaction, and we'll look at different factors that affect the E2 reaction. So I hope everyone's doing really well, everyone's really healthy, and I hope everyone has a great day.